Hello everyone, in this video we'll be discussing the Math 45 Final Exam Review. There are a lot of questions, so I'll just get right into it. Question 1 here asks us to find the equation of the line satisfying each of these three, so there's three parts to this equation, to this question, I should say. And it also specifies in the question specifically, I didn't write it though, that we must write our answer in slope-intercept form. But we'll see that that kind of comes out naturally anyways. Just solve for y basically. So the first thing I want to do is I want to use point slope. That's the main technique to find the equation of a line in general. Use point slope. The point slope, just to remind us, let me write it over here, I guess. Point slope, or IPS for short, is y minus the y value of a point equals m, which is the slope of the line, times x minus the x value of the point. So this point on the line I'm calling x1, y1. Okay, so I want to use this. The only issue with the first part of the question here, though, is that I'm giving 2 points. I don't have a point and a slope, so I can't use point slope directly. But is there a way to find the slope with 2 points? Yes, it's with a slope formula. So the first step will be to find the slope, find m, and I'll do it using, in this problem anyways, m equals y2 minus y1 over x2 minus x1. Think of slope being rise over run. Rise is y's, right, vertical change, and run is horizontal change, so that's the difference of the x's. Now I need to label these points though, so I'll label them each xy, xy. The first one with 1, so x1, y1, and the second one with 2 is x2, y2. That's how it's done. Okay, so now following this, we end up getting m is equal to y2 minus y1, so it's -1 minus -3. So there's double negative, so kind of be careful there. That's going to end up being -1 plus 3, which is +2, over x2 minus x1, that's 5 minus 4, so that's 1. So m equals +2 over 1, so that's just 2 actually. Okay, great. Now we can use point slope. So that's the second step here actually. So don't have too much space, but let's just kind of border this off and say in step 2, I'm going to be using point slope with one of the 2 points. So which point do I rather use? 4, -3 or 5, -1? It really doesn't matter. I'm actually going to use 5, -1. I think that the 1 will make things a little more straightforward, but you can try 4, -3 and check that that works as well. But I'll do this. I'll use this point. And it's important to note that when you're using point slope, you're using the slope m that we just found and a point x1, y1. Doesn't necessarily mean you have to use this. This labeling in red was only for the slope in step 1. Now that we're in step 2, that labeling kind of goes away. So I'm going to relabel this now as x1, y1. So I can use point slope above. So y minus y1, which is -1, equals the slope we just found, 2 times x minus x1. So that's a double negative, so that's y plus 1 is equal to, distribute this, we get 2x minus 10, subtract that 1 to the other side, and we're done. Y is equal to 2x minus 11. Perfect. I guess you can check maybe that plugging in those x values to this equation gives you those y values that those points correspond to, but that's on you if you want to do that. So part B then asks us to find the equation of the line passing through the point -2, 3, but now parallel to the line whose equation is given by this. Now, the word parallel means the slopes are equal. Why is that important? Well, if the slopes are equal, then we can find the slope of the line that we have the equation of, that we're parallel to, and that will be equal to the slope of the line we're trying to find. So in step 1, just like above, same 2 steps. Find slope, use point slope. So with the point given, of course. So I want to find m for the first step, and here I'll do so not by using slope formula like with part A, but instead I'll do so by converting this to slope-intercept form. Slope-intercept form, if you don't remember, I'll write SIF for short, is y is equal to mx plus b, telling us that the number in front of x1, y is by itself is the slope of the line. So naturally I'm going to get y by itself here. That's pretty easy to do, so I'll write that actually, just rewrite it here. 2y plus 3x is equal to 4. Subtract that 3x to the other side, so we get y is equal to -3x plus 4. That's it's 2y, there we go, is equal to -3x plus 4. We just grabbed the 3x and subtracted it to the right. And now divide everything by 2. Those cancel, you get y is equal to negative 3 over 2x plus 2. That 2 doesn't matter. This matters. This tells us that our slope of this line that we're parallel to is negative 3 over 2. But since two lines are parallel, have the same slope, if one slope was different, then it would intersect the other line. Parallel means they don't intersect, so naturally they have to have the same slope. That means that our slope must be negative 3 over 2. Okay, we'll see with part C, it's a little different because of the wording. Parallel and perpendicular, they mean different things regarding slope, but we'll get there when we get there. We're almost there, actually. So step 2 now is to use point slope just like with part A. But now with the only point we have given here is negative 2, 3. Okay, so this point is x1, y1. So now we can use point slope above. I'll box it completely, I guess. Okay, in the box above. So it's going to be y minus the y value equals the slope we just found times x minus the x value. Again, we have a double negative, so it's positive. I'll distribute the negative 3 over 2, and then we'll add this 3 to the other side. Just like that. So I'm going to do this kind of fast, but let's see if we can follow. We go y is equal to negative 3 over 2 times x. That's negative 3 over 2x. Okay, so the double negative is positive 2. Distributing the negative 3 over 2, because we're distributing the sign as well. Negative 3 over 2 times positive 2. Well, the 2's cross cancel, so that's just negative 3. Okay, so it's negative 3 plus 3, but that cancels with that plus 3, so we just end up getting this actually. Kind of strange, maybe you might want to write that out, but it's going to be negative 3 plus 3, and those cancel, so you just end up getting y is equal to negative 3 over 2x. Great. Now part C, very, very, very similar. We're given a point, we're given an equation that we're perpendicular to now instead of parallel to. So unlike parallel, perpendicular means the slopes are not the same, but here the slopes are negative reciprocals of each other, negative reciprocals, sometimes known as opposite reciprocals. And what this means is the slopes aren't the same, but you flip and negate that one slope to get the other slope. And in fact, taking a negative reciprocal of one number will give you back the number you had originally. So if you take negative reciprocal twice, you land back at the same number. So for example, 4 over 5, its reciprocal, negative reciprocal is negative 5 over 4. And the negative reciprocal of negative 5 over 4 is positive 4 over 5. So it gets you back. So that's why I say negative reciprocals of each other. Anyways, jumping into it, step 1, find slope. So how we're going to do that is just like we did above. We're going to convert this into slope-intercept form. So I'm going to grab that 3y to get it by itself. I need to add that 5x to the other side. So we get 3y is equal to 5x plus 9. Divided everything by 3 to get y by itself in this equation. So we get y is equal to 5 over 3x plus 3. That 3 doesn't matter, just like that 2 didn't matter. All that matters is this 5 over 3. Now this is not the slope of the line we're trying to find. This is the slope of the line that we're perpendicular to. So we're going to take the negative reciprocal of this to get our slope. So how do you do that? Well, you change its sign, positive to negative, and you flip the fraction. 5 over 3 now becomes 3 over 5. Perfect. Great. So now, moving on to step 2, we're going to use this point, x1, y1. So use point slope with the given point, 5, 0. So it's pretty simple. Just y minus the y value equals the slope times x minus the x value. Distributing the negative 3 over 5, we get y is equal to negative 3 over 5x plus 3. Why plus 3? Because the double negative, when the distribution takes place, becomes positive, and then 3 over 5 times 5 cross cancels, and you just get 3. And notice y minus 0 is 0, and there we go. I forgot the x, sorry, kind of. There we go. Great, sorry about that. Fantastic. So now, that took a little bit of time, but there were 3 parts there and it was a little involved. So now let's move on to number 2 and let's see how crazy it can get. Right, so for number 3 here, we're asked to find this so-called difference quotient, which actually shows up a lot in calculus. So learning how to apply this, or I guess functions to this, is definitely a pretty important thing, and I think it's nice to see that ahead of time in an algebra class like this one. So right, so how can we get this started? Well, you may notice we could distribute that 3 in. That's fine if you want to do that. Doesn't actually matter. We're going to have to do that anyways, I guess. But more importantly, what does f of x plus h mean? F of x, we know what that means. So we're going to subtract that here. But f of x plus h, that means this x is going to be replaced with this entire x plus h quantity. So very often people like to write this off to the side, which I'll do. So f of x plus h is equal to 3 times 2 minus x. I'll write parentheses and a blank space there, because we're going to replace that x with the quantity x plus h. Notice I say quantity, which warrants those parentheses. Okay? So now we can simplify this. I can distribute that negative. So we get 3 times 2 minus x minus h. I'll also distribute this 3 into these 3 terms. So we get 6 minus 3x minus 3h. Okay. So now let's try to bring things together here. So f of x plus h we know is that quantity. So we have 6 minus 3x minus 3h minus f of x. We need to subtract the entire quantity f of x, so we need those parentheses. I'll distribute that 3, might as well. So we get 6 minus 3x. And then that's all divided by h. Now what we're going to see happen here will always happen with the difference quotient. Basically everything that doesn't involve h on the top will cancel out by subtraction. And then what you'll have left over on the top will have an h, so that it'll cancel with this h in the denominator. So in other words, there's a lot of simplification. So notice, distributing this negative will allow these non-h terms to cancel, right? We get 6 minus 3x minus 3h minus 6 plus 3x, and there it goes. This 3x and this negative 3x cancel, this 6 and negative 6 cancel, so we have negative 3h all over h. I'm going to write it down step by step so that we don't skip steps and get confused. The h's cancel and we get negative 3. There we go. Awesome. So now moving on to number 4. Okay, question 4, I've written something here, but it's actually a lot more wordy and kind of tells a funny story in the actual review. I'll read it here. It says, you want to build a rectangular enclosure for some roosters you have been recently gifted against a shed in your backyard using an entire roll of chicken wire fencing. When unrolled, the total length of the chicken wire fencing is 40 feet long. If you do not fence the side along the shed, what is the largest possible area that can be enclosed? So I've reworded it here. Let's read the rewording. A roll of 40 feet of fencing material is used to enclose a rectangular area that extends from the side of a shed. Okay. If the side of the shed is not fenced, okay, is not fenced, what is the max area of the region? In other words, the region being fenced or enclosed. So let's try to imagine what's going on here. So let's say the shed is this. This is our shed. Okay, so we're fencing some side of the shed. So we're kind of extending that. So this is our enclosed region. Okay. Now notice the kind of shape I've used here. I've obviously made this rectangle, but the lines I drew represent the fencing. This is seen from above. So we have 3 lengths here. And it's a rectangular region. These two have to have the same length, and this is another length. Okay. So you can call these things whatever you want, but since we're using the entire roll of the fencing material, the chicken wire, then it in total adds up to 40 feet. So whatever these you want to call these 3 lengths, they add up to 40. So this plus this equals 40. Now, if you want to call this x, this is also x. Then if you want to call this y, then you'll note that x plus x is 2x plus y, that's going to be 40. So in fact, you can just say y is equal to 40 minus 2x. So in fact, most people just notice that right away, that if this is x and that's x and they add to 40, this is 40 minus those 2. So I'll just write that here. But that would be the calculation if you want to actually write it out and see it like that. So that's nice to know. I'm going to erase it, just for space. So now what we're going to do is we're going to build an area formula, basically an area function. I'm going to call it a of x. Okay, so a of x is going to be the area of this in terms of x. X is unknown. So it's going to be this times that, right? Base times width, or width times length, whatever you want to call it. So it's x times 40 minus 2x. Great. Now expanding out, we get negative 2x squared plus 40x. Of course, it rearranges so it's in descending order. And we notice that it is a quadratic equation. Now, quadratic equations have graphs that are parabolas. The parabola of this equation, the graph of this equation, will be a facing down parabola because of the negative leading coefficient. So we know it's going to go down like this. So that means there's a maximum point. So the x value that corresponds to that would be the length x that corresponds to the maximum area. The y value of this point would correspond to the area itself. So we need to find the vertex of this parabola in order to find the maximum such area. Great. So how do we do that? Well, we know vertex of a parabola is h comma k, where h is negative b over 2a, so maybe I'll write that. Negative b over 2a, and k is f of that. But here I'm calling the function a, so it's a of negative b over 2a. So what's a and what's b? Well, this a and b comes from the ABC notation we usually use for quadratics. Kind of think of a quadratic formula. In other words, negative 2 is going to be a, and 40 is going to be b. A and b. So c is 0, but we don't even need c for this calculation. I need an extra parenthesis there. Good. So let's calculate h, negative b over 2a. That's going to be negative 40 over 2 times a, which is negative 2. So it's a double negative. That's going to be 40 over 4, so that's just 10 actually. Great. So that's 10. So that means x is 10. The x value is 10. So that'll correspond to the largest area. Now what the largest area is a of 10. So what is a of 10? Well, there's a few ways to calculate it, but we have two versions of a. So we can plug it back into this one, but I think the factored version is a little easier to evaluate. So we get 10 times 40 minus 2 times 10. 2 times 10, of course, is 20. 40 minus 20 is just 20. So in total, we get 200, and that's going to be in feet squared, or square feet. And that's, of course, because x is in feet. But I know that because it's 40 feet, so that was the only unit we had. Awesome. So that was number 4. That was really nice to see an application problem, and now we'll move on to number 5. Okay, so for this question, number 5, we're given this rational function, which is a function that is a fraction of two polynomials. We're asked to find all asymptotes, so vertical, horizontal, possibly oblique asymptotes, but I know since the degrees are the same, there's only going to be a horizontal asymptote, no oblique ones, and domain. Now this is kind of tricky actually, because domain you find without canceling at all, but asymptotes you find after cancellation. Why that happens is because any factor that canceled out that involved x would correspond to a hole in the graph, which I may discuss as we go along. So for the first thing I want to do is I want to, well, let's do this. I'll factor top and bottom, but before cancellation, we're going to calculate the domain. Okay. So now notice on the top, they both have a 3, or they all three have a 3 in common. So we can factor that out just by dividing everything by 3. Oh, we can actually divide by 4 on the bottom as well. Factor of 4 out. Okay. And I think I'll write this over here just for space. But the top factors, what two numbers multiply to the last number, negative 6, and add to the middle coefficient, negative 1. Of course, negative 3 and positive 2 do the trick. So that means this trinomial on top factors is x minus 3 times x plus 2. And you can check that, of course, by foiling this out, but that definitely works. And you can see at the bottom, x squared minus 9 is a difference of squares. The square root of x squared and square root of 9 are x and 3. So we're going to write the difference of those numbers and the sum of those numbers. In other words, x plus 3, x minus 3. Okay. Now notice, the x minus 3's will cancel. So hold off on that. That corresponds to a hole, like I mentioned earlier. Before we do that, I'm going to calculate the domain by setting each factor in the denominator equal to 0. How do we do that? Well, if x minus 3 is 0, add 3 to the other side, x is equal to 3. Okay. Similarly, when x plus 3 is 0, that means x is equal to negative 3 by subtracting 3 to the other side. So that means x is not allowed to be these. So why is that? Well, it's because the denominator will be 0. So I'm setting the denominator equal to 0 to get these values, but that implies that the domain is the set of all x values such that x is not equal to these numbers. In other words, these correspond to a 0 denominator, but we don't want a 0 denominator. We want all x values such that there is no 0 denominator. So that's the domain. Now the domain in integral notation, if you're curious, is just negative infinity to, the first one would be negative 3, and then union negative 3 to 3, and then finally union 3 to infinity. So I'm going to box both of these actually. But whichever one you want to use, that's fine. I didn't specify. You know, if you want to use set builder notation or interval notation, probably set builder notation is a little easier to see. The interval notation you can see by actually writing out a number line and then shading everything except for these x values that were not equal to 3 and negative 3. And you'll see that you get these unions of these intervals. Exactly. Okay, great. So now we will notice the cancellation. And after the cancellation, we can talk about the vertical asymptotes and horizontal. I'll talk about vertical first. So the vertical asymptotes occur when the denominator is equal to 0 after cancellation. So set the denominator, x plus 3 equal to 0, so we get x is equal to negative 3. So this equation, x equals negative 3, is the equation of the vertical line that is the vertical asymptote of the graph of this rational function. Okay, what about horizontal asymptote? Well, for horizontal asymptotes, there's actually two cases, really. One where the degree of the top is smaller than degree of the bottom, in which case it's just the x-axis, y equals 0. In the other case we have here where the degrees are the same. Notice x squared highest power on top, and x squared is the highest power on top. On bottom is 2 as well. So the highest power in each numerator and denominator are the same. That's what I call degree. So if you have the degrees that are the same, so this is the second case, then all you need to do is look at the leading coefficients, 3 and 4. Basically what you're doing is taking limits as x goes to infinity, and what you do really is you divide everything by x squared. Those cancel out, so you get 3 and 4 for those first terms, but then dividing every other term by x squared will make it go to 0 in the limit as x goes to infinity. It sounds complicated, but that's the process. So long story short, we get y is equal to 3 over 4. That's just the front number over the front number. When I say front number, I mean the number in front of the highest power. And that only works when the highest powers are the same. The highest powers aren't the same. If the one on top is smaller than the one on the bottom, then it's y equals 0 for the horizontal asymptote. And if the one on top is bigger, you may have an oblique asymptote scenario, or possibly worse, but we're not going to discuss that here. So this, I think, is all we need to know. Great. Now, what was this business about there being a hole? Well, it's kind of weird to explain, but I'll show you the graph at least, because I think we deserve to see that at least. So here's what the graph more or less looks like. So we have x equals 3, x equals negative 3, and then let's say this is 1, so that y equals 3/4 is a little bit below that. So that's y equals 3/4. And this is x equals negative 3. Okay. And the graph of the function, and you can check with your graphing calculator if you want, but it'll look like this in red. So notice it hugs the horizontal asymptote and the vertical asymptote. Now, what was this whole business about the domain not being, you know what? I'm sorry. That was bad. Sorry. There we go. That's the vertical asymptote, not the y-axis. My mistake. So there we go. That's what the graph looks like. But now, what was this whole business about the domain not having 3 or negative 3? So here we can see there's no x value that corresponds to negative 3, but it looks like there is for x equals 3. Well, because it canceled, there's a hole there. In other words, there is a point you can cover to kind of patch that hole up, but that would be the cancellation. So if you were to graph this without canceling, just as is, and opposed to this after cancellation, 3 times x plus 2 over 4 times x plus 3, the graphs will look identical. The real difference is that this includes 3, and this doesn't include 3. So if you plug 3 into this, you get 0 over 0, which is undefined because of the 0 denominator. So 3 is not in the domain of this. But this, after cancellation, you can plug 3 into, and that would correspond to the y value of that so-called hole. There we go. So that's all I wanted to say there. Went a little beyond what we were asked to find in 5, but that was great. So now we'll move on to number 6. All right, so for this problem number 6, we're asked to factor this function over the complex numbers. And so kind of a little bit of a challenge, honestly. This problem may take a little bit of time, and it involves a lot of things. And the question on the review specifically, I kind of mentioned a hint, but we'll see that here. Now the hint is to use the rational zeros theorem, the rational roots theorem. So we'll discuss that in a moment. And I think I also mentioned something to do with using the quadratic formula and what you have left over to find any complex roots. So what we're really doing is finding solutions to this equation, and in noticing the solutions to this equation, zeros of a function really, correspond to factors. So this is the so-called factor theorem, and it says that if x equals a is a 0, then x minus a is a factor. That is the factor theorem. Okay, so now to find solutions, to find x values that work, what we're going to do is we're going to try to use rational zeros theorem. Now, for any function in general, the rational zeros theorem will only give you rational zeros. It's possible you have a function that only has irrational zeros, so it wouldn't work at all. And it may be a lot to do, like it may be a lot of work, so you have to kind of be careful. But here's the rational zeros theorem, right? RZT for short. It basically says to factor your constant term and your leading coefficient, which in this case is just the number 1. Divide all of the factors of the last one by factors of the first one with plus or minuses, and those are going to be your set of possible rational zeros. So let's write that out. So we get this set of possible rational zeros. Factors of 85. So what is 85? Well, it ends in a 5, so it's divisible by 5. And in fact, it's 5 times, not 19, but 5 times 17, actually. So it's 5 times 17. So the factors of 85 are 1, 5, 17, and itself, of course, 85. So if you can't factor it, you always at least get the number itself and 1 as factors. And here the number 1, we only get 1 as its factor, of course, because it's the number 1 itself. So we're going to divide all of these by 1, so we just get these, but with plus or minuses. So we're going to check 1, plus or minus 5, plus or minus 17, and plus or minus 85. Now, how are we going to check these? You can plug them in and see when it's 0, but one of the hints I think I give also is to use synthetic division and show your work with synthetic division, because I think that's a little more efficient than just plugging them in. And it may not seem like that at first because it's a lot to write maybe, but you kind of see that it's a lot of computation power to plug it in. For example, 17 cubed, it's going to take you a while to figure out what that is unless you use your calculator. But synthetic division will make it a little nicer. So let's take a look. So for synthetic division, we need a box number and the coefficients of our function. So the coefficients are 1, 13, 57, and 85. Let me just double check to make sure I'm not missing any signs and everything is indeed positive. Okay, that's fine. So now the box number here will be the number we're testing. So I'm going to test positive 1. Now I don't think that's going to work because everything's positive, so we're not going to get any negatives involved. But just so you can kind of recall what synthetic division does and how the rules work, you bring this first one down for free, multiply by the box number, 1 times 1 is 1, add these, multiply by the box number, add straight down, that would be 71, multiply by the box number, and add straight down, and you get 156 for this one. Now, we want the remainder to be 0, and that would correspond to the actual value, and that's called the remainder theorem. Basically says the remainder, which would be the last number here in synthetic division, is exactly the evaluation you get when you plug in what you're dividing by. Here we're dividing by x minus 1. Kind of corresponds to this. If x minus 1 is a factor, then x equals 1 would be a 0. But it's not. It doesn't correspond to 0. Okay, so that was unfortunate. So let's erase the work here, and then let's continue this again. Try this again, but now with a different number. And now we know that all of the positive ones will not work. And that kind of makes sense because all of these were positive. So I'm going to cross out the positives and only focus on the negatives now. So now let's try negative 1 and see what happens. Bring this one down for free, multiply by the box number, add straight down, multiply by the box number, add straight down. So that's going to be less than 85, and then when you multiply by negative 1, you'll get a negative, but it's not going to be 0. In fact, if you think about it, this will only be 0 if this would result in a negative 85. And clearly whatever this is times negative 1 is going to be less than negative 85, or greater than. You know what I mean. It's going to be a number whose absolute value is smaller than 85. So negative 1 unfortunately doesn't work. Let's try negative 5 now. So we kind of know the endpoints, what those look like in the synthetic division. Let's see. 1 times negative 5 is negative 5. If you add these, you get 8. 8 times negative 5 is negative 40. And look at that. Add these, you get 17, and we already said 17 times 5 was 85. Times negative 5 would be negative 85 indeed. Perfect. So what this really tells us is that when you divide this function by x minus negative 5 or x plus 5, then it actually, when you divide it by that, you actually get this remainder 0. So this corresponds to the quadratic x squared plus 8x plus 17. So what we've really shown is that this function, let me kind of border this off a bit, can be written as x plus 5 times its quadratic, x squared plus 8x plus 17. And if you want to check at this point, FOILing this out, or multiplying this out, and see that it gives you this indeed, then you can check that, but it definitely does work. But now we want to find the solutions of this, the zeros of this. So why is this x plus 5 again? Because remember, if x equals a is a 0, then x minus that's a factor. So x equals negative 5 is a 0, so x minus negative 5, which is x plus 5, is a factor. So now I want to find the zeros of this, and we can do that using quadratic formula. You can also try to do a repeat or repetition of synthetic division using these values, but they're not going to work. This will actually have complex solutions, as it turns out. And the kind of hint there is that I'm asking you to factor over complex numbers, so we expect complex numbers to come up somewhere, and that of course comes up in a quadratic formula. So this is 1x squared plus 8x plus 17. So we have a, b, and c are going to just be 1, 8, and 17 respectively. So from quadratic formula, we get negative b, x is equal to negative b, which is negative 8, plus or minus the square root of b squared, it's 8 squared, minus 4 times a times c, all over 2a. So you can review that if you want, but I'll write it here actually. So quadratic formula says, just to remind ourselves, if ax squared plus bx plus c is equal to 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Perfect. Okay, so let's see. I'm going to do this radical kind of off to the side. 8 squared I know is 64. Let's see, 4 times 17. Well, if you double 17, you get 34, and if you double that again, you get, let's see, 34 doubled 68. So it's going to be minus 68, which is negative 4. Okay. So all in all, this is negative 8 plus or minus the square root of negative 4, all over 2. Now, what is the square root of a negative number? It's imaginary. So the square root of 4 I know is 2, so the square root of negative 4 is going to be 2 times I, the imaginary unit. So we get negative 8 plus or minus 2i, all over 2. So what I'm going to do is I'm going to factor 2 out from the top. So factoring the 2 out from the top, we're left with negative 4 plus or minus I on the inside, over 2. And now that factor that we pulled out, that 2, cancels this 2, and we're left with this. Negative 4 plus or minus I. Which means we have two solutions really. X is either equal to negative 4 minus I, or x is equal to negative 4 plus I. So these are our zeros, so that means the factors that these correspond to are x minus these. So the factors would be x minus this, x minus that. So if you distribute the negative, you get positive 4 plus I, positive 4 minus I. So that means this factors as x plus 4 minus I times x plus 4 minus I. And then the x plus 5 factor comes down, and we have completely factored our function over the complex numbers into what are called linear factors. So there's no powers on x. Fantastic. So that was kind of long like I said it would be, but there it goes. That was 6. Now let's move on to number 7. Okay, great. So number 7 here is asking us to solve each of these. We have a logarithmic equation and 2 exponential equations. Now, these are actually going to be pretty quick. For these problems, what you basically do is you convert into the opposite form. So logarithmic form, we convert to exponential. So remember how to do that. We have the base 2x to the power 3, so all to that power is equal to the inside of the log. So logarithm solve for powers, and the base of the log is the base of the exponential. Good. So now if you take this power to each of those, you get 2 to the third, which is 8, times x to the third on the left side is equal to that 8 on the right. Dividing by 8, we get x cubed is equal to 1. Cube rooting both sides gives us x is equal to the cube root of 1, which is just 1 itself. Perfect. Okay, now what? Now for b, well, there's a few ways of doing this. If you want to convert this to logarithmic form, you can. We have to combine these. What I want to do instead, actually, is I want to use this method of uniqueness, so a one-to-one property of an exponential, of the exponential function, really. So I'm going to combine these into one exponential involving x, and then write this as the same base. So I'm basically going to write everything with the same base. I'm going to notice here that 3, 9, and 81 can all be written as powers of 3. You may think 81 is 9 squared, but 9 is 3 to the second. So that means 81 is 9 squared, which is 3 squared squared, so it's 3 to the 4th. So 9 is 3 squared, so that's that to the x. 3 to the 3x minus 1 still, it doesn't change. And then this is 3 to the 4th. Okay, so now multiplying these two, we get 2x, but then adding the exponents, we get 3 to the 2x plus 3x minus 1 is equal to 3 to the 4th. You combine these, you get 5x, so that's 3 to the 5x minus 1 is equal to 3 to the 4th. So the uniqueness property, or one-to-one property, basically says that when the bases are the same, the powers are the same. The only exception really is when the base is like 1 or 0 or something funny like that. Like 1 to the 3 is equal to 1 to the second, for example, but 3 is not equal to 2. But if your base is positive and not equal to 1, then this property holds. So we get 5x minus 1 is equal to 4, and you can check that x equals 1 satisfies that. Add 1 to the other side, you get 5x equals 5, and then dividing by 5, we get x is equal to 1. Perfect. So I'd be pretty freaked out if x is equal to 1 would be the solution for part C. That's, of course, a joke. This is coincidence that they're a repeat. That's not going to happen here, actually. So what I want to do here is I want to actually convert this to logarithmic form. That's because you can't really write 2/3 and 20 as powers of e. You can, kind of, but it involves using the natural logarithm anyways. So what I'm going to do is I'm going to multiply both sides by 3/2 to get that e to the 3x by itself. So multiply with the reciprocal of 2/3, which is 3/2. That'll cancel out that 2/3. It's being multiplied to our power of e. Notice that 20 goes into, well, 20 divided by 2 is 10. So 2 goes into 20 is what I meant to say, 10 times. So we end up with e to the 3x is equal to 30. Okay, pretty simple from here. Converting this to logarithmic form says that log base, our base e, of 30 is equal to the power of that logarithm, which is 3x, or power of that exponential, I should say. So then dividing by 3, we get our answer. Now, obviously, log base e has a different name. It's ln. So dividing by 3, we get x is equal to log base e, ln of 30, divided by 3. But I'm going to write that as 1/3 ln of 30. Fantastic. So that concludes number 7. Now let's move on to number 8. So for number 8, it's also a solving problem. We're asked to solve these equations, but these are kind of oddball equations in my mind. This is a rational equation. This is kind of like a radical equation in some sense. Right? Well, I guess you can think of it as a rational exponent equation. But x to the 1/3 is the same thing as the cube root of x. So you can think of this as a radical equation. But that's the only term, notice, involving x. The only thing involving x is x to the 1/3. So I'm going to get x to the 1/3 by itself and then take both sides to the third power, which will cancel that 1/3 because it's like multiplying by 3 in the power. So to do that, I'll add 5 to the other side to get 2x to the 1/3 is equal to 6. Dividing by 2, we get x to the 1/3 is equal to 3. Perfect. So now I'm going to take both sides to the third power, like I said. Why? Because that cancels the 1/3 in the exponent. Kind of multiplying the powers, 3 times 1/3 cancels. So those cancel out, we get x to the 1, which is just x, equals 3 to the third, which 3 times 3 is 9, times another 3 is 27. Perfect. Not too bad. Now b is a little more complicated in my opinion, and that's because we have these rational things. Now what you can do actually, because of the 0 on the opposite side, is you can actually subtract this fraction to that side, cross multiply, and then go from there. That I don't think would be a bad idea, but to be more general, what I'm going to do actually is I'm going to factor the denominators, look for the LCD, multiply everything by the LCD to cancel denominators, and to solve that equation we get with no denominators. So how do these factor? Well, here we can pull an x out. We get x times x minus 3. And here, this is the difference in squares, which of course is factors as x minus 3 times x plus 3. We actually saw that, I think, exactly earlier in the review, didn't we? Great. So what's our LCD now? Our LCD is going to be kind of the culmination of these. So what do you need from each of these to kind of combine into one common denominator? Well, if you look at this one, from this denominator, what we don't have in the other one is the x plus 3. We already have the x minus 3 here, but we don't have this x plus 3 from the other one. So I'm going to include that here. So this is going to be x times x minus 3, but now times an x plus 3. And notice the LCD here includes both of the factors from the other one. So kind of think of how you would combine into one common denominator. You would multiply top and bottom by what you need from the other one. So this needs an x plus 3, that would need just an x, so you end up getting this with the least common denominator. So now what I like to do is I like to multiply each of these parts of the equation, which are 3 parts really, and 0 on the opposite side, by the LCD to cancel the denominators. Now when you multiply this by the LCD, the x and x minus 3 factors cancel, so the top 4 is just multiplied by x plus 3. So we get this. Okay. Similarly, for this term, we get 1, which is the top, times what didn't cancel with the LCD. X minus 3 and x plus 3 cancel, so we're just left with 1 times x, which is just x, and of course 0 times anything is 0. It's probably a good time to mention that values that will not work are ones that leave you with a 0 denominator when you plug them back in. And we can actually check that when the LCD is equal to 0, we get x would be equal to 0, 3, or negative 3. So that means these cannot be values of x in our solution because that would correspond to a 0 denominator, and it wouldn't actually be a solution. So those are for extraneous solutions. So hopefully we don't get that as a result here, but let's, I guess, continue to find out. So distributing this 4, we get 4x plus 12 plus x is equal to 0. These combine to 5x. Subtract that 12 to the other side, divide by 5. So we don't get any of those actually, fortunately. So we end up with x is equal to negative 12 over 5. And if you want to check this, you can actually check both of these by plugging them in. In fact, any equation you can check by plugging it into the original. And that would help to check for extraneous solutions, if any, but these both work. Great, so that was 8. Now let's move on to number 9. All right, so for this problem number 9, we're asked to find if there's an inverse, and if there is, find the inverse. So for this function here, there actually is an inverse. And you can kind of consider graphing a rational function like this that has a vertical asymptote at 3, right, when the denominator is 0, and a horizontal asymptote at 0 because the degree of the top is smaller than the degree of the bottom. And you can see if you look at something like that, just by kind of graphing it really quickly, it will actually look flipped because it's minus. It's kind of a little hard to explain, but if you pull the negative out from the bottom into the outside, you end up with this. So it's actually flipped. This is actually below, but that's kind of beyond the point. The whole point is looking at the graph. This passes the horizontal line test. So it's a one-to-one function, therefore it has an inverse function. Okay. Now how do you find the inverse function? Well, how we find the inverse function is by replacing f of x with y, swapping x's with y's, and solving for the new y, and then relabeling that as f inverse of x. So just before we move on, let me just say yes, there is an inverse. So does it have an inverse? Yes, it does. How do we show that? Well, it passes the horizontal line test. Let me write that actually. passes HLT, short for horizontal line test. You can actually also just try to find the function and see if there are any pluses or minuses or anything like that. Because when you have a plus or minus, that means it's not a function because there's two outputs for a given input. So it's nice to see those ideas combined. So here's the process. We're going to replace this with y. It's kind of the first step of the process. Then we swap x's with y's. That's the swapping part. And then we solve for y if we can. Now in this case, it's pretty simple to do so. In fact, there's a lot of ways you can do it. You can cross multiply and then divide by x, or you can just kind of swap these. Or you can flip both sides even and then multiply by 2. But I'll multiply both sides by 3 minus y. So 3 minus y times the quantity x is equal to 2. You could distribute the x if you want and then subtract 3x and divide by negative x, but actually dividing by x works. So we get, I don't know why I canceled that, sorry. So we get 3 minus y is equal to 2 over x. So all we have to do now is get y by itself by subtracting 3 and then multiplying by negative 1. There's another way you can do this by actually adding this y to the other side and then subtracting 2x. So let me show that. So if you add y to this side, that goes away. And then if you subtract 2x over to the left, then we get y is equal to 3 minus 2x. So I'm, of course, kind of flipping things after solving for y, but that's a nice way of seeing it. Now that we're here, we can replace y with f inverse. So finally, the final step in this process is to write f inverse of x equals 3 minus 2 over x. Now, if you want to write this with a common denominator, you can. It would be 3x minus 2 all over x. And it was kind of nice, you can check this by plugging in values for x. And the result you would get would be the input of this that would give you the value back. So it's almost like, kind of describing it weird. But let's say we start with a number, let's do the opposite. So let's start a number that we're going to plug into f. Let's just keep it simple, let's say 0. Which actually isn't super simple as it turns out. But when you plug in 0 into f, you get 2 over 3 minus 0, that's 2/3. So that's why it's not super simple, because 2/3 is kind of a complicated number. But if you plug it into f inverse now, what do you get? Well, you should get 0 back. So f inverse undoes what this did. In fact, that kind of explains why the process worked, because swapping x's and y's is swapping inputs for outputs. And you're basically saying that the output of f is the input of f inverse that'll give you an output that was the input that gave you that output for f. It's kind of complicated to say the words, but that's what it is. Now, if you plug that in here, 3 minus 2 over 2/3, well, 2 over 2/3, that's the same as multiplied by 3 to clear denominators. That's the same as 6 over 2, which is just 3. So you get 3 minus 3, which is indeed 0. So that checks out. Now, that's not a rigorous proof that they're inverses, but we picked 0 at random. So if you pick any number, it'll actually work. You can also take the composition of these functions, and you'll see that you get x in the end. In either order, you take the composition. Okay, this one is a little interesting because x squared is a quadratic. Its graph is a parabola. X squared minus 3 is that parabola shifted down 3 units. So we get this, which of course very miserably fails the horizontal line test. So there's no inverse function. If we were given a restriction like x is bigger than 0, then it's only this right half of the parabola, and that would actually pass the horizontal line test. And that would actually, believe it or not, but it would actually have an inverse function. But this doesn't. So the answer here is no, and that's because we fail the horizontal line test for this function. Okay. Now if you wanted to actually do this, I'll show you. Just going through the motions and trying to find the inverse, you can actually show that it doesn't have an inverse as well. So replace f of x with y, swap x's and y's. To solve for y, you can add 3 to the other side. And at this point, to get y by itself, you can square root both sides, but when you square root both sides of an equation, remember that you get a plus or minus. So the radical and square cancel, but then you get y is equal to plus or minus the square root of x plus 3, and those are two outputs for the given input x. So if you plug in 1, you get the square root of 1 plus 3, which is 4, but y would be positive 2, sorry, the square root of 4 is 2. You get positive 2 or negative 2. So you get two outputs for an input. So you actually are not a function. You fail the vertical line test. Which makes sense, because if your function fails a horizontal line test, then reflecting it about the line y equals x, which is supposed to give you the graph of its inverse function, would actually fail the vertical line test and not actually be a function. So it's almost like this is an inverse relation of this. So that idea will work, but it's not a function. So we can't give it the inverse function name. Okay. So that was nice to see those two ideas mesh together. So that concludes 9. Now let's move on to number 10. Okay, so for number 10 here, we're asked to solve each of these systems of equations. We're also asked to actually state the method we use. And the only methods we've learned for these solving the systems of two equations, the main methods anyways, were substitution or elimination. And the way you can tell which one you should probably use, and you can use either honestly, but the way you can tell which one you should probably use is if one of the variables is already isolated, you can substitute that expression for that variable in the other equation, so that's substitution, or if you have everything on one side, so it's like in standard form in both equations, and you can just multiply the top by a number that'll match the opposite of the other coefficient of that variable to cancel when you add straight down by what is called elimination. So what I've described exactly is substitution for this one and elimination for this one. Y is by itself here for the second equation. And in fact, I like to label these. I'll label this as equation 1. And this is equation 2. I'll do the same here. So equation 1 has y by itself, so I'm going to actually substitute that into 1 for y. So anywhere I see a y, which is right here, I'm going to replace it with this quantity. So we're going to write 5x minus 4y, but y is 2x plus 3 from the other equation, is equal to negative 15. Okay, distribute this negative 4, and we can actually solve for x. By the way, let me write here that we're using substitution. Okay. So we have 5x minus 8x minus 12 is equal to negative 15. Pretty simple to solve. Add 12 to the other side. Combine those to negative 3x. So we get negative 3x equal to negative 3, divided by negative 3, then we get x is equal to 1. Which is not our solution, but it's part of our solution. Okay. And now we'll plug this back into either of these, but plugging back into equation 2 is the, I think, better idea. And that's, of course, because y is already by itself. So when you plug it into that, you get y already. So for equation 2, we get y is equal to, so just using this guy, we get y is equal to 2 times x, which is 1, plus 3. So that's 5. So y is equal to 5. That's another part of our solution. So altogether, our ordered pair solution is the x value 1, comma the y value 5. Awesome. So now for number 10 part B, well, we don't have y by itself, and you could, if you wanted to, solve for x or y. Like for example, you can add 7y to the other side and divide by 2 to get x by itself, but you get fractions and it gets kind of messy. So in this case, what's better to do, I think, is actually multiply the top by 5, and you can see that the x's will cancel that way, so you get 10x minus 10x, and those cancel out. Now you can also multiply the top by 8 and the bottom by negative 7. That'll cancel out the y's. But of course, the numbers get pretty large there, so I'm not going to go that route. What I'm going to do is I'm going to eliminate x's, solve for y, and then plug that y value into one of these to find x. So let's write out what we get here. So distributing that 5, multiplying everything by 5 that is, we get 10x minus 14y, 5, so it's 35, sorry, mistake. 35y, there we go, equals 16 times 5, that's going to be 80 for the first equation. Second equation remains the same, negative 10x minus 8y is equal to 6. So hopefully adding these we get something nice. So these cancel out. Let's see, 35 plus 8, that's 43, negative 43. Y is equal to 86, which is actually double 43, so that's nice. So when you divide by negative 43, we get y is equal to negative 2. Perfect. So now we can substitute this back into either of these two equations. I want to actually use equation 1, the original equation 1, before multiplying by 5. And why that is because the numbers are smaller there. And since we're solving for x, the last thing we're going to do is divide by the number in front of x. I'd rather divide by 2 than divide by negative 10, but I don't think it actually matters. You can try plugging this into equation 2 and see what you get, but I'm going to plug it into equation 1 like I said. So we get 2x minus 7y, which we now know is negative 2, is equal to 16. So that means 2x plus 14 is equal to 16. Subtract 14 to the other side, we get 2. So 2x is equal to 2, divided by 2, we get x is equal to 1. So our ordered pair solution here is the x value we got, comma the y value we got. And I probably should mention that we used the method of elimination to solve the system of equations. Fantastic. So that completes number 10, and now let's move on to number 11. Alright, so for this problem here, we're asked to solve another system of equations, but this time it's a system of 3 equations with 3 variables, which is usually a doozy. And the way I'm going to solve this is, well, first I'm going to do what I did in the previous ones. I'm going to label these equations 1, 2, and 3. There are multiple ways of solving these kinds of things. You can use basically a mixed bag of elimination and substitution to solve for things. I'm basically going to use elimination in 2 different ways to eliminate one variable, 2 different ways, to result in 2 equations that do not involve that variable that we eliminated. Then I'm going to get those 2 equations, convert them into a system of equations, or combine them into a system of equations with 2 variables only, solve that using the methods we saw in number 10, and then once I have a solution for that, we can plug those 2 values back into one of these 3 to find the remaining variable. Sounds like a mouthful, but let's just get to it. Now, the one I want to eliminate is x. Now, how I can tell is because there's no number in front of x. So I can multiply by negative 2 to eliminate with this, and by negative 3 to eliminate with this. Z is actually a good candidate as well, because you can multiply this by negative 3 to get positive 6, which will cancel with this, or by negative 1 to make it positive 2z, that'll cancel with this. So you can eliminate z actually, if you want, but I'm going to eliminate x. So the first step here in my process is to eliminate x 2 different ways. So I'm going to eliminate x with equations, let's use 1 and 2 first. So I'm going to do that by multiplying equation 2 by negative 2, so I can cancel that 2x from equation 1. So I'm going to multiply the bottom by negative 2. So first let's write the top equation. 2x plus 3y minus 2z is equal to 7. Multiply the bottom by negative 2, again negative 2x, negative 10y, positive 12z, and negative 2 times that's negative 6. Perfect. Add straight down, the x's cancel. We get negative 7y plus 10z is equal to positive 1. Now I want to keep this result. I'm actually going to call this equation 4. It's a new equation. Okay. The other part of this step is to eliminate x a different way. So now I'm going to eliminate x again. Same variable x, but now with 2 different sets. Of course, one of them has to be the same because we only have 3 to choose from. So we can choose 1 and 2 or 2 and 3. But I mentioned we have to use 2 because of the free agent, right? There's no number in front of x. So I'm going to multiply 2 by negative 3. So again, I'm going to use equation 2 and 3 by the way here. Multiplying equation 2 by negative 3, we get negative 3x minus 15y plus 18z equals negative 9. Multiplying everything by negative 3. Okay. Bottom one stays the same, equation 3 stays the same. 3x plus 3y minus 2z is equal to 5. Add straight down here, these cancel, we get negative 12y plus 16z is equal to negative 4. And this I'm going to call equation 5. So now combine these 2, that's our second step here. Now I'm going to solve this new system involving 4 and 5. So I'm going to solve the system. Negative 7y plus 10z is equal to 1. That's equation 4. And negative 12z, you know what? Just to make matters a little easier, I'm noticing here we can divide by 4. So I'm going to divide by, I'm going to divide by negative 4, okay? So let's do that. Let's divide this by negative 4, and then I'll call that result 5. What you can do in any equation, you can just divide through by a number to simplify things, just so we're not using numbers that are too large. So we get positive 3, negative 4z, and positive 1. So that's equation 5. 3y minus 4z is equal to 1. So now maybe here it's a little more obvious what we can eliminate. Of course, we can multiply the top by 3, bottom by 7 to eliminate y. But I think it'd be easier to eliminate z by multiplying the top by 2 and bottom by 5. So let me write that. Multiply the top by 2 to get 20z, bottom by 5 to get negative 20z. So those will cancel. So in doing that, we get negative 14y plus 20z is equal to 2. Bottom becomes 15y minus 20z is equal to 5. Adding straight down, the z's cancel like we said they would. We get y is equal to 7. So we have a part of our solution. So now what we do, we plug it back into one of these equations to get z. I'm going to plug it back into equation 5, let's say. So we get 3 times y, which is 7, minus 4z is equal to 1. So it's 21 minus 4z is equal to 1. Subtract that 21. We get negative 4z is equal to negative 20. Divide by negative 4. Double negative is positive. 20 divided by 4 is 5. So z is equal to 5. Whew, nice. One last step here, and that's to plug back in to one of these three. So I'm actually going to write this step up above, if that's okay, just because of space, and I don't want to go to another board or use this tiny space below. So step 3 now is to plug these solutions in to find our remaining one. So substitute to find x. And that'll finish off our ordered triple x, y, z. So let's plug into equation 2. X is by itself. It has nothing in front, so we don't have to divide by anything there. So for equation 2, we get x plus 5y. We found out the y was 7. Minus 6 times z we found to be 5. Okay, equals 3. So altogether, that's x plus 35 minus 30 is equal to 3. So I've kind of run out of space still, but we get, that's 5, subtract 5. 3 minus 5 is negative 2, so x is negative 2. So our ordered triple then is the ordered triple negative 2, comma the y value we got, comma the z value we got. Now, if you want to check this answer, you can check this by plugging these x, y, and z values into each of these three equations and seeing that they all check out. Okay, so that concludes number 11, and now let's move on to number 12. Okay, so here we're asked to find the center and radius of the circle whose equation is given by this. Now this is not standard form for a circle, but just to remind us, standard form for a circle is x minus h squared plus y minus k squared is equal to r squared. And what's nice about this is the center is just h comma k. What's subtracted from y and x. So change the sign of the things next to x and y and you get the center. Square root the thing on the other side and you get the radius. So the radius, of course, is r in this case. Okay? So kind of keep that in mind. So now, to get this form, we need to basically complete the square for x and for y. So I'm going to group the x's and y's together in their own way and complete the squares by performing the completed square trick. So here are y's and x's. The negative 11 we don't need, so I'm going to actually throw that on the other side by adding it. So we have x squared minus 4x plus something that will complete it to a square. Y squared plus 2y plus something else that will complete that square. Equals at 11 we're adding over, and then plus these two things, extra things we're adding to the left. So of course we have to add them to the right to balance the equation. So now if this is a completed square, it's going to be x minus half of 4, which is 2. Why is that? Well, that's how you complete a square, basically. You half the middle term if there's nothing in front of your square term. So notice, if you expand this out, x squared minus 2x times 2, because you double that, you get negative 4x indeed, and then negative 2 squared is positive 4 for this last guy. So we're going to add 4 to both sides from this one. Great. What about for y? Well, very similarly, that'll complete as y plus half of 2, which is 1, squared. Here it was negative because of negative 4. Here it's positive because of the positive 2. And these are added together. Now notice when you expand this out, you go y squared plus 2y plus 1. So we need to add 1 here. 11 plus 4 is 15 plus 1 is 16, which is 4 squared. So I'm going to write that here below just for space. So altogether we have that our center is the point, which is a sign change of the numbers next to x and y. So sign change of negative 2 is positive 2, sign change of positive 1 is negative 1. Square root of 16, of course, is 4. So the radius is 4, and the center is the point 2, negative 1. Great. Now, if that part kind of confused you with the sign change thing, basically I'm setting these equal to 0 and solving for x and y, but really it's just recognizing that it's x minus h, y minus k. And it works. X minus 2 is x minus 2. Y minus negative 1 is y plus 1 because of the double negative. Great, so that concludes 12, now moving on to number 13. All right, so this is an interesting question. Here we're asked to give the equation of a parabola with the vertex and focus. This vertex and this given focus. Now, there's two different equations for a parabola, and it all depends on if you have a vertical parabola or horizontal parabola. So does it open to the left or right or up or down? Now, since these both have the same x value, there's no x change, there's only a y change, vertical change. So that tells me this is indeed a vertical parabola, and the vertex is h comma k, so it's going to be x minus h, y minus k, and the distance from the vertex to the focus, which you can just tell is 1, multiplied by 4 will be multiplied to the factor that's not squared. So you can actually do this without graphing. That's kind of what I'm trying to say, but it's a little hard to follow, right? So let's graph and plot these points. So if we do that, 6 comma 1, 1, 2, 3, 4, 5, 6, yep. And then 1, 2, 3, 4, 5, 6, let's say. So we only need 1 and 2 though. So that's 6, 1 and that's 6, 2. That's our vertex and that's our focus. So the shape will clearly look like an upward parabola. So we know that it's vertical and we know that it's facing up. So it's a vertical parabola and it faces up. Okay, great. So what does that mean? Well, for vertical parabolas, we have the equation y minus k and x minus h. For vertical parabolas, x minus h is squared and y minus k is multiplied by 4p, where p is the distance from the vertex to the focus. Now, p is negative if it would face in the negative direction, but it's not, it's positive here. So notice the distance here is just the difference between these two numbers, like I mentioned earlier, and that's just 1. So I know p is 1. K and h are the coordinates of the vertex, which of course are 6 and 1. So 6 is h, and k is 1. Now, the way I describe this makes it really easy to write out what it is for a horizontal parabola. The 1 that's squared is y minus k in that case, and 4p is multiplied to the x minus h factor in that case. Now remember, if the parabola opens in the positive direction to the right, p is positive, but if it opens in the negative direction to the left, p is negative. And the actual value of p, that's not the sign part, just the absolute value, is the distance from the vertex to the focus. Okay, great. So now we're done. We have 4 times 1, which is 4, times y minus 1 equals x minus 6 all squared. So now all I'm going to do is solve for y. This is, I guess, kind of acceptable, but we can do a little more. So I'm going to solve for y completely. Let's distribute some things here. That's if you factor this out, you get x squared, or FOIL this out, I meant to say. X squared minus double 6 is 12x, and then 6 squared is 36. Add that 4 to the other side, we get 4y is equal to x squared minus 12x plus 40. And then finally, divide everything by 4, we get 1/4 x squared minus 12 divided by 4 is 3, plus 40 divided by 4 is 10. Fantastic, there we go. So that concludes 13. Now let's move on to number 14. Okay, so here we're asked to write the first 5 terms of these sequences. A is, I think, pretty straightforward. We're given a general term, so we just plug in n equals 1, 2, 3, 4, and 5, and see what we get as the terms, and that'll be it. B, we're given a1, which is the first term, and d, which is the common difference. So here, b is actually assumed to be an arithmetic sequence. So you add 3 to the first term to get the second term, and repeat that addition of 3 to get all the subsequent terms. So it's arithmetic. Let me write it out completely. Okay. Now, kind of similarly, C has R, which is known as a common ratio. So instead of arithmetic, this is a geometric sequence, which is very much the same, only instead of adding the number to the first term to get the second and so on, you multiply by. So we multiply a2 by r to get a3 and so on. But of course we need a1, so we have to think what multiplied by this will give you a2, so basically we divide. But we'll get there soon enough. Let's move on to a. So I'm going to let n equal 1, When n is equal to 1, we get 1 squared minus 1, that's 0. 0 over anything 0, so that's 0 for the first term in the sequence. When n is equal to 2, we get 2 squared minus 1, that's 3, over 2 squared plus 1, that's 4 plus 1. It's kind of interesting because n squared is the same. So if you square 2, you get 4, right? So 4 minus 1 over 4 plus 1, that's 3 over 5. Okay. When n is equal to 3, 3 squared is 9, so it's 9 minus 1 over 9 plus 1. So that's actually going to be 8 over 10, right? But that reduces to 4 over 5. So I'm going to reduce that, actually. When n is equal to 4, well, when n is equal to 4, 4 squared is 16. 16 minus 1 is 15. 16 plus 1 is 17. That doesn't reduce, so that's just 15 over 17. And one more for n equals 5. 5 squared is 25. 25 minus 1 is 24. And 25 plus 1 is 26. That also reduces by dividing by 2, just like the n equals 3 case did. And that's going to be 12 over 13. Now this sequence goes on and on and on, but we're only asked to find the first 5 terms, so there they are. 0, 3/5, 4/5, 15 over 17, and 12 over 13. Perfect. Now for B, we're going to start with A1, which is 3, and then we're going to add 3 to get each subsequent term. So here A1 is 3. To get A2, we add 3. To get A3, we add 3 again. We get 9, plus 3 is that, plus 3 is that, plus 3 is that, plus 3 is that. You can keep doing this forever, obviously. But we're only asked to find the first 5 terms. So I obviously took a little overboard. So let me box the first 5. You can actually also generate the general term using the formula for arithmetic and also for geometric sequences. So that's nice, and you can look into that if you want. And I think we'll see more of that maybe in the next few problems, but I'm not going to do that like this here. I'm not going to do it like that. Okay, so for geometric, the tricky thing here is that A1 is skipped, and then we have A2. And then we multiply by the ratio 2 to get the next term. Multiply by 2 again, multiply by 2 again, multiply by 2 again, and multiply by 2 again. Now, the first 5 terms will actually end at 24. Okay? But what times 2 is 3? Well, of course, it's 3 divided by 2, so this is 3 halves. Perfect. So there are the first 5 terms, and now let's move on to number 15. Okay, so here we're asked to find the sums of these things, and I have each of them written in sigma notation. Now, for the last 2, I'm going to use formulas. I'm going to use formulas we've developed for arithmetic sequences and geometric sequences. Well, for sums of those. Sum of arithmetic sequence and a sum of the geometric sequence. Now, how I can tell that they're those types of sums or those types of sequences, we'll actually see when we write out a few things. But A is going to give us the idea that we can just plug in the first few terms and then add those. And in fact, you can do that if you want. But for B and C, I really want to use the formulas because, well, there's a lot more terms in these two than there are in this one. So let's see. So first off, what do? We start with I being equal to -1, then plug in the next integer after -1, which is 0, then 1, then 2, then 3, then 4, then 5. So for these two, we start at 1 and go to 8, start at 1 and go to 19. Okay, so I'm going to plug in -1. -1 squared is +1, minus 2 times -1. That's a double negative, so that's 1 plus 2, that's 3. Okay, that's when I is equal to -1. Okay, now when I is equal to 0, we get 0 squared minus 2 times 0, that's just 0. Plus when I is equal to 1, we get 1 squared is 1 minus 2, that's -1. And in fact, I believe the other ones will all be negative. Actually, maybe not. They actually turn positive, I think, after a while, because the square actually dominates after multiplying by 2 at some point. In fact, when you plug in 2, they're the same, right? 2 squared is 4, and 2 times 2 is 4. So that's going to be 0 as well. Okay. When I is equal to 3, I've kind of run out of space to write all of the I equals, but I'll just write the terms we get. So when I is equal to 3, we get 3 squared is 9, minus 2 times 3 is 6, so that's 3. It's nice to see some symmetry here, actually. Okay. And then when you plug in, that's 3. When you plug in 4, 4 squared is 16. Minus 2 times 4 is 8, so that's going to be 8. And then finally, when I is equal to 5, we get 5 squared is 25. Minus 2 times 5 is 10. So it's going to be 15. Great. So all I'm going to do here is just, well, add all of these terms. And again, you can do B and C this way. Plug K equals 1 through 19, get all those 19 terms, add them together. Plug in J equals 1 through 8 to these, add all those terms, and then you get the result for those. But again, I want to do these ones a little differently. But here, I'm just kind of showing that. The reason why, by the way, we're doing this like this and these with formulas is because we don't actually have a formula for a quadratic sequence. There is a formula, but we just haven't discussed it in class. It's kind of a little too involved. But let's see. So these combine to 6 plus 0, of course, doesn't matter. Minus 1, that's 5. If you add 5 to 15, you get 20, and then that to 8 is 28. So the result here altogether is a whopping 28. Perfect. Now what? And now onto this one. I'm going to write out the first few terms to notice that this sequence is arithmetic. And you can tell because it's a linear sequence. There's a number in front of k added to a number. So it's a linear expression. Similarly, this is exponential, so this is a geometric sequence. So when k is 1, you get negative 3 minus 4 times 1, that's negative 7. When k is equal to 2, that's negative 3 minus 8. That's negative 3 minus 8, that's negative 11. And I should write a plus in between these, not commas, sorry. So it's negative 7 plus negative 11. There we go. Plus, when you plug in, that's 1, 2, when you plug in 3, that's 12. Negative 3 minus 12 is negative 15. And you can clearly see that we're adding negative 4 each time to get to the next term in the sum. Now, you can tell ahead of time that's what's happening because it's a negative 4. So I know this is indeed an arithmetic sequence, or an arithmetic sum, really. Now, we actually have a formula for an arithmetic sum, and the formula is that S sub k, which is the sum from A1, A2, all the way up to AK of an arithmetic sequence, is k times A1 plus AK all over 2. So k is the number of terms, right? A1, A2, A3, all the way up to AK. So here we're going to have 19 of them, 1 through 19. So k is 19 here. So this sum, all the way up to the last one, we can plug in, so AK is going to be A sub 19. So you can plug in 19 and see what it is. So negative 3 minus 4 times 19. 4 times 19, that's going to be, let's see, double 19 is 38, double that is going to be 76. So it's negative 3 minus 76, it's going to be negative 79. So if you add 4, or I guess really subtract 4, total 19 times, you'll get this. Well, I guess you're doing it 18 times, but you know what I mean. So this result should be, according to the formula, k, which is 19, times A1, which is this guy, plus A19, which is this guy. So it's negative 7 plus negative 79, all over 2. So it looks like it's a fraction, which is weird, but notice 19 is odd, so it doesn't cancel here. But negative 7 minus 79 is actually even. Right? It's kind of like 7 plus 79, that's 86. So that's negative 86. So this ends up being actually 18 times negative 86 all over 2. 2 goes into 86 43 times. So that's negative 43 times 19. Let's see, I don't want to use a calculator here, but 19 I know is a little less than 20, right? So this is kind of like 20 times 43. So you can think of this as 21 times 43. If we distribute that, we know 20 times 43 is 86 with a 0, minus a 43. 60 minus 43 is 17, so it should be 817. And it's a negative, of course. There we go. And you can also check that when you add all these numbers together, you do get indeed negative 817. Just going to double check my work here real quick. Seems okay. Yeah, so I'm gonna call it there. I think that's okay. And now we'll move on to C. Now C, well, it's geometric. So let's write out the terms and see what happens. So when you plug in j equals 1, 1 minus 1 is 0, 2 to the 0 is 1, so you just get 5. Plus, when j is 2, 2 minus 1 is 1, 2 to the 1 is 2, 2 times 5 is 10. And you kind of see when you plug in each number bigger than 1, so each subsequent integer following 1 for j, you get powers, consecutive powers of 2. So we have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. So it's 5 times 1, 5 times 2, 5 times 3. So, sorry, I said that kind of weird. 5 times 1, 5 times 2, 5 times 4, 5 times 8. Because it's 5 times 2 to the 0, 2 to the 1, 2 to the 3, 2 to the 4, and so on. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the second is 4. So 2 times 4 is 20. 2 times the next multiple of 2, or power of 2, is 8. So it's going to be 40. But notice this follows exactly the pattern multiplying by 2. So this is indeed geometric. Times 2, times 2, times 2. So this is a geometric sum. Now we actually have a formula for a geometric sum, much like we did for an arithmetic sum. And if you want to find what the last term is even, you can do that as well. Notice when j is 8, a minus 1 is 7. 2 to the 7th is 128. And 128 times 5 is, I think, 640. I think it's 640. You can check that. I mean, I guess you can kind of see it. Doubling this a few more times, you see 40, 80, 160, 320, 640. So that should be the 8th one. Okay. So, right. So, again, it's not too far off because here I have 5 of the 8 terms, so we're just missing those 3, which I just said, right? 80, 160, 320. So this is not hard to do this way. If you want to do it that way, you can do it that way. That's fine. But I want to show the formula. So for arithmetic, we had this. So that's if it's arithmetic. But if it's geometric, S sub k, where a sub n, the sequence a sub n, is a geometric sequence instead, we end up getting this formula. So it is r to the k minus 1 over r minus 1. And I think I'm missing something. I think there's like there's a1 multiplied to this actually. Yeah. So let's see. So a1 is going to be the first term, which is 5, times r to the k, which is 8. So that's r is 2, by the way. So it's 2 to the 8 minus 1 over 2 minus 1. Great. Now, what's interesting here is that 2 minus 1 is 1 in the denominator, so this is just 5 times whatever 2 to the 8 minus 1 is. Now, 2 to the 8, I said 2 to the 7th was 128. 2 to the 8th is going to be 256. So 256 minus 1 is 255. So what the heck is that? Well, again, I don't want to use a calculator, so I'm just going to do this by multiplying by 250 and 5 and then adding those. There's probably more elegant ways of multiplying by 5. In fact, one nice way is to think of 5 as 10 over 2. So you can half this and then multiply by 10. So like I know half of 250 is 125. And half of 5 is 2.5. So it's going to be 1275. So that, in fact, is the answer, 1275. Well, which I didn't mention above too much, but you can kind of tell. These are all negatives, so we expect the sum to be negative. So that makes sense that it's negative. And again, you can check by adding all those if you want that it is the answer. Now this ends in a 5, which is kind of striking, but these all end in a 0, the exception of the first one. So that actually does make sense and lines up. Great, so that took some time actually, but now let's move on finally to the last problem of the review, number 16. Okay, so for number 16, finally, we're asked to find the 5th term of the arithmetic sequence, whose 12th term is 60 and 20th term is 84. Now, there's actually quite a few ways of doing this, but the way I like to show usually, I like to show 2 ways actually. I like to show the kind of intuitive way, where you just write out a bunch of terms and try to kind of feel around for what things are. So let's actually do that first. So we have 20 terms total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 3 more, 2 more, 5 more. I think that's 20. I'm just going to call that 20. In fact, I kind of want to make this somewhat accurate so we can kind of count. It may be a little bit of a headache the more terms you have, but this idea kind of holds. And you can kind of generalize this, put dots in the middle, and kind of count by subtracting the positions you're at. But let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the 20th term isn't 20. 20th term is 84. Okay. The 5th term we want to know, so that's this guy. So this is the one we're trying to find. And the 12th term, let's see, that's going to be 6, 7, 8, 9, 10, 11, 12th term is 60. So we know those two. How can we find this one? Well, we can actually find all of them, believe it or not, given 2. The reason why you can do that is basically, believe it or not, but it's basically because if you have 2 points on the line, you can find the equation of the line, and thus you can find every point on the line. Why is that? Well, I kind of mentioned it earlier. An arithmetic sequence has a general term that's linear. I said that earlier, actually. So what that means is that the general term of this arithmetic sequence is a linear equation, and we basically have 2 points in this linear equation. We have 12, 60 and 20, 84. So you can use those points to find the equation of the line, and then plug in 5 to find the point that corresponds to x equals 5. Believe it or not, that's basically what's going on. And I'm going to show that in kind of a different way after this. But let's count. So we're in the 12th position here. We're in the 20th position here. We're going to the 5th position. So the first thing I'm going to do is I'm going to count how many of the common difference we need to add to get from 60 to 84. And we can develop this relationship between them. So notice, to get from this to the 13th one, we have to add the common difference d. You add it again, and so on. We do that all the way until the last one. The question is, how many of these d's will we need to add to go from 60 to 84? Well, it ends up, long story short, just being the difference between the positions. 20 minus 12 is 8. So in fact, there are indeed 8 jumps you need to go from 60 to 84. So what we end up developing is this fact that 60 plus 20 minus 12 is 8. So 8 of these d's will give you 84. So you can solve for the common difference. Backtrack this, and then you'll get the 5th term. So subtract 60, you get 24. 8d is equal to 24. Divide by 8, d is equal to 3. Aha. So now what? Well, now we can backtrack, because if you think about it, to get from this guy all the way over to that one, you have to add d how many times? Again, it's just the difference in the positions. 12 minus 5 is 7. So if you add 5d to this one, you get, or 7d, I should say, to this one, you get 60. So now we get this relationship that a5 added to 7d is equal to 60. But we know d is 3, so this is really 7 times 3, which is 21. So subtract 21 to the other side. We get our final answer for a sub 5, which is 39. So that is the answer. I'm going to write that over here, 39. Okay. I want to show a slightly different way of doing this, and I think I can do it in the space we have here. Now, the first thing I want to do is, so I'm not doing it this way anymore. It works, but it's very, takes a lot of space, or a lot of counting and visualization. So non-visually, I'm going to actually use these facts and use our notation. So what do I mean by notation? The 12th term is 60, using notation of sequences that we've developed, is A12 equals 60. Similarly, A20 is equal to 84. Okay. Now we also have a general term for an arithmetic sequence, and the general term is A sub n is equal to A1 plus d times n minus 1. Now, there's a lot of different ways of writing this. One way I like to do this actually is to distribute the d. So you get a1 plus dn minus d. And then if you combine these, Notice a1 plus d would be a2, a2 plus d is a3, so a1 minus d would be the term before a1 if there was a term before. So I very often like to call it a0, so I think it's nicer to write it like that because you can kind of see that this indeed is a linear relationship. So an is equal to dn plus a0, where a0 and d are just numbers. So kind of think of like mx plus b. Very, very similar. So I'm going to write each of these in that way using the fact that when n is equal to 12, we get a sub n, which is a sub 12, really, is equal to d times 12 plus a0. So it's 12d plus a0. Okay, similarly, when n is equal to 20, we get a20 is equal to 20d plus a0. So you may think, how does that help? Because we really haven't done too much here. But notice, what is a12? A12 is 60. What is a20? A20 is 84. So really we get a system of two linear equations. We get 12d plus a0 is equal to 60. And 20d plus a0 is equal to 84. So in fact, this is just a system of equations. When we know how to solve these, we can just subtract to cancel the a0s. So we get 12 minus 20, which is negative 8d, equals, that minus that's negative 24, divided by negative 8, you get d is 3. Perfect. Plug back in to find a0. That's going to be, let's plug into the top one. We get 12 times 3 is 36. So 36 plus a0 is equal to 60. So if you subtract, you get a0 is equal to 24. So that means our equation, this guy, our general form, or general term, there we go, a sub n is really 3n plus 24. So that means a5, well, what we're trying to find is when n is equal to 5, which is 3 times 5 plus 24, which, look at that, it's 15 plus 24, which is exactly 39. Nice. Okay, so that was nice. It's two different ways. Definitely less intuitive, less feeling around, more of like an actual systematic procedure you can follow, which is nice. If you didn't quite like this, you can use this form here above, but they're really the same thing. I'm just taking advantage of this kind of newer notation. I think it's nicer and it's easier to work with, but that's just me. It's not generally shown. Okay, so that concludes the review for the final exam for Math 45. Really hope you all enjoyed it and understood and were able to follow all of my crazy explanations with all these problems. Also, I really hope you enjoyed the class. I myself really enjoyed teaching this class. I really hope you enjoyed my explanation of things and the reviews I've given you for the exams as well. And with that being said, I wish you all luck on the final exam for Math 45, and that's it.